Hi, everybody. So we've talked a lot about how to think about and recognize these transformations. The rest of this review is going to focus on actually performing the transformations. So first, we're going to look at some single transformations. In the next next sequence of videos, we'll also be looking at compound or composite transformations, right? So we are approximately here at page 5, I believe, and we have to perform this transformation given this rule. Well, the first thing we have to do is recognize the rule we've been given. Now, there's lots of different giveaways, and depending on your teacher, they may have emphasized different things. And so, even though the R is going to be associated with reflection, the big giveaway, the thing you should really be focused on, is the fact that this is a line. Most specifically, is going to be what we call the line of reflection. And I'm going to abbreviate here just to save a little time and space, right? So once you see that you have a line, and even though it's not an axis, let's recall that y equals 1 is actually going to be a horizontal line passing through the y value of 1. Okay, and again, your teacher may have emphasized it different ways, but there are two other groups of lines besides the y equals mx plus b and, of course, the x and y axis. If you have a y equals, it's always going to be horizontal, and if you have an x equals, it's going to be vertical. So in this case, our line of reflection is y equals 1. I pre-written out like the description because this is like the internal dialogue you should have in your head. If you see that R and you see that line of reflection because it's not a vector, you should absolutely 100% be thinking it's a reflection. In my class, we kind of talked about it being like up down, which is kind of like a horizontal reflection, or left right, being a vertical being a vertical reflection, just to kind of conceptualize how this thing is going to move. But anyway, we do have a reflection. It is over y equals 1, which we have now drawn out in the graph. It's just an issue now of actually reflecting. There are rules associated with the reflection of this type, but honestly, it's easier just to count. We know that we have to hit this line of reflection at a right angle with our mapping line, and the line of reflection has to bisect at a perpendicular angle those mapping lines. And to recall, what I mean is this: if you take like B and you count to the axis, 1, 2, 3, 4, it's 4 units from the axis and at a right angle, and so to travel away from the axis, the same amount. And that's what I mean about perpendicular bisector, because if you look at this line between B and B prime, it is a right angle, and it's exactly 4 units long, ergo each side of that's going to be the same distance. And we can repeat that logic for all of them. So if I'm taking C, I can move 2 to the axis at a right angle, 2 away from the axis, and that masks my C prime. For my A, 1, 2, 3, 4 to the red line, 1, 2, 3, 4 away from the red line. Okay, and that'll give me my placement, for A prime. So connecting our new image vertices, we see a triangle that is rigid, meaning that it kept the same size, same shape, but simply flipped over the line. Okay, and that's where we have this A prime, B prime, C prime. All right. And that's really as easy as reflections are. Just in terms of a quick review. Okay, if we look at the mapping lines, meaning the lines that connect the original image points and their primes, it should always be at a right angle to the line of reflection, and the distances here should always be the same. And so it's definitely true between C and C prime, but it should also be equally true if I look at the A prime line. Okay, definitely at a right angle. Also, we can notice the distance to the red line from A and the red line to A prime are the same. And that's how you can really map a reflection. Okay, so second on this page. Again, I kind of pre-wrote out what's going on, just to save time. But again, like the big thing about knowing that this is a translation is not just really that T, but it's the fact that we have this vector. The vector is the thing that gives it away, because unlike a line, a vector is going to give you a distance and direction. It's literally going to tell you how this shape is going to slide across the axes. And so we do have a translation by vector 8 comma negative 6. Well, remember the first number is the x direction, the second number is the y direction. So if the x direction is 8, I know it's going to be plus x, hence right, and I know it's going to be negative 6 for the y, it's going to be down because that's going to be the negative y direction. In terms of mapping a translation, we just have to count out precisely how much to move up, over, left, or right. Okay, and so if I take any of these points, say like Bravo here, point B, I just have to move it how my vector says to move it. So I move over 1, 2, 3, 4, 5, 6, 7, 8, and then I'm going to move down 6. So 1, 2, 3, 4, 5, and 6. Because really, even though we're translating the entire shape, we're really translating kind of a point at a time. And so we just repeat. So for point C, 1, 2, 3, 4, 5, 6, 7, 8. Then now 1, 2, 3, 4, 5, and 6. Now, one way you can check ourselves along the way is that these two vectors, these two red lines that define how much we're citing, these should be congruent and they should also be parallel. And at least checking by the eye test, I think those pass. Like those look fairly parallel and look about the same distance. Okay, and so we're repeating with the A to the A prime point. So 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6. And again, this one should be parallel. It should also be congruent as well. All right. Okay, so in terms of where our shape ends up, we have A prime right here. We have B prime. We have C prime. And D prime is a little hard to see, but it's going to be here at this point 3, 0. Okay, that's going to be our D prime point. Now, as I connect these points and make our new image shape, the thing we're definitely looking for is that we have a rigid motion. Rigid motions, if you recall, by definition, preserve distances in terms of lengths and angles. In other words, the beginning and ending shape should be congruent. The term preserve, again, I don't know if you heard this a lot in class, because all the teachers are different. I don't always use that terminology myself. But when you hear the word preserve, it means keep the same. And so that's really the idea of rigid transformations, is that you are going to keep the beginning and ending shape the same. In this particular case, you're keeping the beginning and ending of the shapes the same by sliding along these parallel congruent vertices, or vectors, excuse me. And so you may see markings like this. This is just to confirm that as we're moving along these red lines, all the red lines are precisely the same. Okay. Let's keep going. I think there's 6 total like this, and so they're all kind of in the same type of problem, so we should just continue, right? Here we have another reflection. Again, the giveaway is going to be not just its R, but the fact that we have a line of reflection right here. Okay. Again, we don't have a line of reflection that's going to be one of the axes. Instead, it's going to be y equals negative 5. Y equals negative 5 is going to be another vertical line. So right here is going to be our y equals negative 5 line. I missed a little bit. Let me move that down. Move the hand. Yeah, there we go. Okay, so our line of reflection is going to be right through the middle of our shape. So the points are going to be flipping up and down depending on where they are located relative to the beginning. Relative to the line of reflection. But we still have to follow the perpendicular bisector rule. Okay, and so what I mean is this. If we take point A and we draw a line to the line of reflection, please notice that it's 2 units long and it hits line of reflection at a right angle. And so we copy that on the other end. It should also be at a right angle, also 2 units long. And that's going to help us locate our A prime. We can do that for B. So this time we're traveling up to the line of reflection, but we should also travel the same amount, 2 units, and also at a right angle, and that should locate our B prime. And then our C is going to travel downward to the line of reflection, 2 units, and then 2 units away, and that should be our C prime. Okay. As long as the red line of reflection has perpendicularly bisected these 3 mapping lines, we can be fairly certain that we end up with the right shape. The second way we check is we actually look at the second shape, the image shape, if you were, and we ask ourselves a critical question, is this congruent? In other words, is it a rigid motion from the first shape? Okay. So the purple triangle compared to the red triangle certainly looks like it's going to be the same angles and the same line segments. Okay, and then so we can be fairly sure that the reflection came off correctly. All right, let's keep going. Okay. So here we have something that's not a triangle, but this doesn't actually change the rules. It doesn't change what we do. The first thing we should establish is what kind of transformation this is. Well, if you've been kind of following my logic so far, you know, even though the arc gives it away, the y-axis, the fact that this is a line, makes this a line of reflection. So for me personally, I always like to draw the line of reflection in. The y-axis is an axis that goes up and down. And so that's going to be my line of reflection. And so now the work is simply moving these points manually because it's really the best way. So B to B prime shall be perpendicularly bisected. So there's my B prime point. 2 units to the axis, 2 units away from the axis at a right angle. Okay, so A goes 8 units to the axis. So we should travel 8 units away from the axis at a right angle, making the purple line perpendicularly bisected by line of reflection. Point D travels 1, 2, 3, 4 units. So 1, 2, 3, 4 units again. That's our D prime, right angle, definitely. Same distance because we definitely counted that out. Okay, and this is not cooperating, but there we go. Point C. Okay, so 8 units to the axis, 8 units away from the axis. That should be our C prime. All right, so let me zoom out just a touch. Okay, so now we have all our endpoints. Let's connect them. So C connects to D, D connects to A, to B, and then back down to C. I'm taking advantage of like the Kami's digital ink tools. That's one of the reasons I like the program so much, is that it's quite easy to kind of navigate. Oops, not you. Okay, so here's kind of our new shape compared to our old one. Okay, and so the perpendicularly bisected like mapping lines are a good indicator that we did this properly, but really we should look at our beginning and ending shape and make sure that it is the same size and shape. It preserves side lengths and angles, and it looks like it reasonably does. Okay, we move on. Okay, I think there's one more set here of single transformations, and we're going to get into our composites next. Okay, and so this is all old hat. So really, we kind of isolate ourselves just to do 2 of these transformations. So it's really going to be a translation or a reflection. Here we see that we have a vector. Okay, and so that means we're going to have the side translation. In this case, -6 moves it left 6, and then +8 moves it up 8. Because remember, this is the XY change. And so we're going to have these vectors. So I'll take advantage of the shape tool here. What do you say? Red vectors? Let's do it. Okay, so we take any of these points. Let's say like point E. We're going to move it 6 units left. So 1, 2, 3, 4, 5, 6, and then up 8 units. 3, 4, 5, 6, 7, 8. Okay, and then really all the vectors should do this. Okay, so if I go to point F, we're going to move 6 left, and then we're going to move up 8. And if I look at those 2 vectors, they should be parallel and they should be congruent. And I think they could reasonably call them that. Okay, so we move over 6 and then up 8. That should be parallel and congruent to the first ones. Over 6, up 8. Okay, and again, we should see this like consistent, parallel, and congruent. And so these should all be the same length, and they should all have the same slope. Okay, and you saw me count them out, and that's really how we're confirming it, because if they all count the same, that means they have the same change in y and change in x, which means they do have the same distance and same direction as well. Okay, so in terms of mapping this bad boy out, let's see. We have h prime right here. This is going to be our e prime. That's going to be our f prime, and that's going to be our g prime. And so last step, let's actually outline the shape really well. And we're really just trying to make sure that we feel like we did this rigid transformation correctly. That's an exact copy of the original, but moved in some way, either by reflection or by translation. Okay, so I'm going to do a little quick highlight color here. There we go. Okay, and those would be our translated, in this case, quadrilateral, because it's four-side. Okay, one last one. Here we have a reflection over the y-axis, again, because we've been given this line of reflection, a line right here. So it's an issue of first mapping that line out. Okay, it's a y-axis, so it's going to be the vertical axis. Let's go a little bit thicker on that. It's hard to see. Okay, so it's going to be that as our line of intersection. I'm sorry, line of reflection. And so let's do some mappings here. All right. So B, 2 units to the axis, 2 units away. That's be our B prime. We have 4 units to the axis, 1, 2, 3, 4 units away from the axis. Not the straightest line I ever drew, but I mean, we're just trying to represent it here, right? So that's A to A prime. Okay, and so the shape. Okay, well, B and C. I can't do that. Let's go back. Change that thickness. Let's try that again. Okay, so C prime to A prime to B prime back to C prime. Okay, and so we have this triangle as our new image triangle. Okay, and again, it's reasonably preserved in terms of angles and side lengths. I can definitely say this was a rigid motion, a reflection. Keep in mind one last time on these single transformations. Okay, that we have a perpendicular intersection at each mapping line, and then we counted them out, but we know the distances here are going to be the same. There we go. So definitely a reflection. All right, so in the next section, guys, I believe we're going to get into composite functions. Yeah, so we actually have to perform some composite functions based on the rules. But I'm going to stop this video here. I'll see you guys in the next part. Only 2 parts left, composite functions, and then we're going to move on to actually like predicting composite functions, and that'll be it. All right, thank you.